have any questions related to lab 6. So you lead the session. Lab 6, any question?
Yes, I have a question about the last part. We did many measurements, بس إنه ما عرفت ليش we did them. إنه don't we use بس تبع x equal to 0?
So I'm opening, I think this is it. So you said lab 6, x equal to 0. Where is it? Where is it? Okay, RC, so this is it.
It is the last table.
Okay. The last table is about the magnetic field inside a flat coil, or am I wrong? Okay, and you have x, position is x. And x is equal to 0 only at position x is equal to 0. So if you go back to the equation, which is few slides above, it is an equation in terms of x, and x is a variable. The question, so I'm talking about this equation. X is the position from the center. So at a distance x from the center. So x is the distance away from the center of the coil. And it's exactly the same distance you see in the table. So at x equals 0, you can replace x by 0 and use this magnetic field. Compare the value of the magnetic field at the center of the coil to the theoretical one. So center, yani x equals 0. All right? Did I answer your question?
So we don't need any of the other values, no?
At the center. Apparently, they don't trust a lot the magnetic field away from the center, or they simply want you to calculate it at the center. Compare theory with experimental only at the center. Yes?
When you mention comment, إذا طلع معي result accurate, should I mention anything about the errors?
So usually comment, we talk about precision, we talk about accuracy, we talk about sources of errors. And sometimes we simply analyze the difference, or comment sometimes would go under the umbrella of linear, not linear. But here, there supposedly should be equal. So there's nothing to analyze but the fact if they're precise or not, accurate or not, and list the sources of errors, because if not accurate, it's due to some sources of errors.
Is my mic on?
Yes, it is.
I want to know, is that accurate and precise? Should I mention about sources of?
Yes, one student in the previous section told me that one day she got 0% difference, 0% difference. And she said, shall I list the sources of errors in this case? I told her, sometimes you have 0% difference due to the fact that the measuring tool is not precise at all. So let's say your mass is approximately 50 and the theoretical value is approximately 50. Since you don't have enough information, you see that the percentage difference is 0 because you don't have enough information, not because you are very precise or because you are very accurate. You see? So this is one reason that would give you 0% difference. Also, 0% difference may happen if you have two sources of errors that would cancel, their effects are canceling each other. For example, source 1 will give you a positive difference, source 2 will give you a negative difference. You may end up with 0 difference. This doesn't mean there's no error. Probably those errors, they have some effects, some canceling effects. So 0% difference doesn't mean no source of error. You have a lot of errors in your experiment and you are aware of them, irrespective of the value you get for percentage difference. Do I make sense? Do you agree with me? You don't have to agree.
Yes, yes.
You don't have to agree.
I have a question in part C. Yes, I agree. I said it, but I don't know if you heard me.
I heard you, yeah.
In part C, tuna diameter, but I did not know, why we should use it, and I didn't use it.
You don't have to use it. Because in the equation of magnetic field, there's no diameter. It's only it's only a general measurement. I want to say to piss you off, but no, really, it's just a random measurement. So we usually do all the measurements we have in front of us, and we use only what we need. And you see, the equation, I think I remember why they want the average, because in the old days, we used to give the students the equation not at the center. This is only at the center, right? we used to give it at any position, and any position is related to the angle, and the angle is related to the radius and the length. So this equation is only applicable when you have a length very much bigger than the radius, or a length going to infinity, and this is only applicable at the center or for a very long length. So if the length is reasonable and not infinite, in the equation you will have radius 1 and length and some theta related cosine, whatever. So we just reduced the equation, but we did not change the lab report. That's why they asked you to find the diameter. But anyway, we usually do a lot of measurements and we pick only what we need. Okay?
I have a question.
Yes, Dana.
Regarding the first table, the answers were plotted according to 3 significant figures. However, for example, in the magnetic field, the error is 0.1. So do we need to adjust the answers in order to have only 1 decimal place?
Let me see if I understood well. Your position has 1 decimal and the magnetic field has 1 decimal. What do you want to adjust? The X and Y axis are independent. Like they shouldn't have the same precision because each was measured using a different measuring tool. Am I right?
Yeah, but I was talking about the error because the answers, like for example, plus or minus 0.1, but the answers were plotted to have like 2 decimal places. So should I like remove 1 decimal place from the answers, from the results?
The table you mean? Are you talking about part A? Yes. So in part A, I just realized there's something creepy in here. The length is measured with a regular ruler, and the regular ruler should give you 2 decimals, which means you have to add a 0 in here. Now for the magnetic field,
doctor,
أنا
my table منا هيك, my table فيها 2 decimal places بالdistance.
Okay, so أنا ظبطتها, بتذكر ظبطتها.
ايه دكتور ما انت بعتي لنا الريزلتس لانه
I modified. Alright, so Dana, you're not happy about the values in the table, or is it the values you calculated from the plot? Because there's nothing to calculate.
No, I was talking about the magnetic field. The magnetic field,
in the table.
Results, they have 2 decimal places, so but the error on the magnetic field is 0.1, which has only 1 decimal place. So I was saying,
how do you know the error on the magnetic field? Let me find the
I was going to ask the same question. It's the least, the smallest digit. It's digital decimeter. So it's 0.01. Why?
Okay, let me check. I'm opening the results. And I want to know, how do you know the error on the magnetic field? Who gave it to you? Was it me? Is this the file I sent you? Just a second.
Yes. No, you just said it's digital decimeter that we used. So how do we do it?
Okay, so I can see the error is 2 decimal.
Yes,
measure digital decimeter. But I need to understand the confusion of Dana. Probably I wrote something that confused her. So Dana,
no, I think,
how do you know?
So the error has 0.01, not 0.1.
Yeah, but how do you know the error? Who told you what the error is? Is it you assuming?
So, yeah, I assumed it was 0.1. Okay. It's my mistake.
So Dana, you assumed something and then you got confused. So your assumption is wrong.
Yes.
Okay. No, I thought probably there's something I said in the video, you know? All right.
Yeah, also another question.
Yes.
If you could go back to part A, please. Here, the average diameter of sound, do we need to get the error through RMS, alpha RMS?
All right, so this question is twofold. First of all, they never asked for the error, but some students want to find the error to be able to know how to round. So this is not a real average. A real average is when you do many trials of the same exact thing, and then you find the average. Here, you measure the outer diameter and the inner diameter, and they are 2 different measurements. So what they mean by average is the median, like the midpoint or the mid diameter. So which is basically, you add the outer to the inner, you divide by 2. And for you to find the error on it, you need to do propagation of error and not RMS, because it is a simple calculation. Okay? Although they don't want you, they never ask you to find the error. It's up to you to find it or not. Some students, They go crazy if they don't have the error. They want the error because they need to know how to round. But if they don't ask you to do the error, you can simply be reasonable. Diameter 1 is 2 decimals, if I'm not wrong. Diameter 2 is 2 decimals. So I'm gonna take the, no, not only you, Jean, I received a lot of questions about this. So I was saying that the average would be 2 decimals if you wanna be reasonable, okay?
Okay, thank you.
All right. But yes, you can find the error, and the error is not the RMS, it's propagation of error.
Doctor?
Do you want to meet Yara, my daughter?
Yes,
Of course.
She is stealing chocolate. Do you see her? No, she's not stealing. I'm joking. She's taking chocolate. So this is Yara. She's in grade 10. I mean in grade 5, and she is 10 years old.
حلو اسمي.
وين Yara? Okay, Yara. So every time Yara send me a text message, I would think my daughter is calling me from the bedroom, and I freak out. Yeah, you guys, you can go close the door behind you. I'm sorry for the interruption. All right, back to your questions.
Doctor?
Yeah.
I had a question in question 2.
Plot, or you mean the next table?
No, it's the first table.
Okay.
I plotted and I found no
position of the center.
Yes, طلعت بالنص.
Okay.
But I didn't really know what I should write in the comment section of the question.
All right. So basically, you realize from the plot that the center is where the maximum magnetic field is. And then,
yes, I realized.
Okay. And then from the theory, you know that the magnetic field is maximum at the center. So you simply compare. If you got the same position, maximum magnetic field at exactly the center, usually from the graph, you can tell that the magnetic field is maximum at position 7, let's say. And then you realize that the center is at position 6. And you say there's a slight difference between the graphical center, or the center we found from the graph, and the center we know. So in your case, if it's exactly the same, just say, I know they're supposed to be the same and we got them similar. It's okay. You don't have to discuss more. Okay?
Okay. Thank you.
دكتور أنا كمان كان عندي سؤال بيشبه هيدا أنا عن الكومنتينج على الجراف. يعني حسيت ما بعرف إنه شرحتها بس رجعت يعني حسيت إنه الشرح مش enough يعني بس كتبت.
So probably the question is trivial because the values given to you, they actually lead to the exact center, right? So probably. But Anna, I love this question. I love the compare. It has a lot to say. You can list the similarities and the differences and come up with a very interesting conclusion. Conclusion related to something proportional to something.
Doctor?
Yes?
I will compare and طلعت معي on the same plot, like a graph which is a little bit longer and stuff. So I started comparing these stuff.
Yes, exactly. So it's obvious the compare is what's similar, the shape, what's similar, the center, and that's it. What's different, it's the magnitude of the different values. And what's interesting that the magnitude is double, exactly double. And you can prove.
Yes, and I use the number of turns.
Yes. And you can see it in the equation, so it's obvious. I know the equation works only for the center, but this equation that would work for any position of the probe is very similar. In other words, it's still proportional to n. Okay?
I have a question.
This is a very interesting session. My first session, nobody asked me anything about lab 6. Yes, go ahead, George. Please ask.
About the magnetic field. It's in millitesla.
Yes.
Do I have to take it as Tesla for the SI unit to respect it? And now when I'm doing the slope and the error on slope.
All right. So basically, George, to answer your question, I would say nobody has the right to boss you and say use SI unit unless you're dealing with big constants. For instance, if I go back to this equation and I see there is mu0 could be your boss. In other words, mu0 would force you to use SI units. all right? Because mu0 has SI units, otherwise you need to convert it, which means if you're simply plotting, not using mu0, you can keep it centimeter millitesla. You want to find the slope, it's going to be in millitesla per centimeter. You want to find anything you want, it's okay. But when you want to use the equation and you want to use mu0, this is where mu0, your boss, is going to say, you know, you have to use SI unit. Otherwise, nobody has the right to boss you. You can use non-SI units, all right?
Okay. Yes.
Some students would say, Miss, I'm confused and I'm too scared to use non-SI units. I would say use SI units to stay on the safe side. Those students usually get confused when they have constants and non-constants, and you know, combining centi with milli, two different prefixes, could lead us to some confusion and mess. All right, if you are aware of the mess and you're in control of it, keep it. Centimeter is very nice because nobody wants 10 to the -2, you know, and 10 to the -3. But if you believe you can get confused easily, use SI. Okay?
Yes, for the error of the slope, if I use Tesla, it's times 10 to the power -5. If I use millitesla, it's 10 to the power -2.
Thank you so much. We are doing physics lab, and those prefixes are there for a reason. Let's keep them. Let's fight for them. I know in the course we don't use them. We hate them. In the lab we love them.
Yes. Okay.
All right. Anything else related to lab 6? It's a very interesting lab. It's one of my favorites. I have many favorites. Talking of favorites, optics 1 is also one of my favorites. It's too easy, it can get boring though. Okay, but it's very interesting. Shall we move to lab 7?
Yes.
All right. If you remember anything related to lab 6, just throw me an email, okay? All right, so lab 7, the due date is Wednesday, November 18, and not next Monday. The reason is I want to create a nice recording of the experiment, and I don't have one. I also have one created by other instructors. I will try not to use it unless I have no choice and LAU is locked down for real, because observations in this lab is very important and it has a lot of descriptive nature. So it's good for you to have a very good video of the experiment for you to be able to enjoy this lab. The outline is the following. You will notice that optics 1, lab 7, is divided into 4 mini experiments. Reflection, that you already know from grade 9. Flat mirror. You never studied cylindrical mirror unless you did the American high school, and I know probably none of you did American high school. By cylindrical mirror, I mean concave and convex mirrors. You will get introduced to those in the course, but whatever we need in the lab now is very introductory. So a simple definition would be enough for you. Snell's law, you already know it from high school. It is also called Descartes' law. It's the one responsible to tell you what is the angle of incidence and what is the angle of refraction for light as it moves from a medium to a different transparent medium. Dispersion, probably you described that in high school. I'm gonna discuss it in a moment. Total internal reflection is a very sensitive topic, like tricky topic that I want you to understand well. That deals with the fact that sometimes refraction does not occur and all the light will reflect and stays inside the medium, all right? So let's tackle the theory and the experiment at the same time. This is part 1. Probably I'm gonna open the chat. Some students may be saying something. All right, so experiment 1, part 1, the reflection plane mirror. You will be given something like that. It's a metallic object. It has a flat section, a curved section, and another curved section. I will be using this for a flat mirror. This is for a concave mirror, and this for a convex mirror, and I'm gonna explain spherical mirrors later. This is a box that will give me a ray of light. You have a regular lamp inside, not a laser, so it's gonna be white light, like a beam of white light. It's gonna hit this surface and get reflected. I have a white paper under my equipment, and I can, with a pencil, trace the rays and the surface or the mirror, the surface of the mirror, okay? I can see the incident ray, the reflected ray. I draw the normal. I can measure with a protractor this angle and this angle. This is a real view of the experiment, although this is not the experiment done in the lab because I never had a flat mirror like this one. I've been using something like that. You will see it in the video, hopefully next Monday. Here, they show you the law of reflection. This is a reflective surface. This is the angle of incidence. By definition, it's the angle between the incident ray and the normal, not the surface. This is the angle of reflection. And the law of reflection states theta I equals to theta R. Okay? This is the lab report. They want you to rotate your mirror and find 3 different trials. Measure angle of incidence, angle of reflection, repeat, repeat. What is the relationship between both angles? You think about it following the law and your values. And then they ask you about 3 colored rays. There's a button on the light source that would give you many colors instead of one white light. You simply rotate the filter and it gives you red and green and blue, probably, I can't remember, or yellow. So you need to answer the question by simply observing the video. Are the 3 colored rays reversed left to right by the plane mirror? So watch the video and try to answer the question. Okay? Next, experiment 1, part 2, reflection, but now using cylindrical mirror. Okay? I'm gonna start with a concave mirror. This is a concave mirror. 1 second. This is a concave mirror. First question is, you're supposed to trace the surface of the mirror and complete the circle and use a regular ruler to measure the radius. Okay? So if I were you, I can simply, I don't know how you will do this and I don't know how I can communicate it with you, but usually the students will use this mirror and they will move the mirror parallel to itself a bit until they form a full circle to find the radius. And then you will use 5 beams on the concave part of the mirror. The 5 beams will reflect into the focal length because it's known, focal point I mean, let me use a pen, because it's known when the rays are parallel to the optical axis and the optical axis is in green. By definition or as default, the rays will actually meet at the focal point. So you can simply observe the incident rays and the reflected rays, and you can mark with a pencil where they meet, and you can say this is the focal point. Now with a ruler, you can measure the focal length, which is here, which is the distance between the focal point and the surface of the mirror. Okay? For the case of the convex mirror, the rays do not meet, they diverge. So you make them meet on the other side of the mirror on a paper with a pencil. And where they meet is going to be called the focal point. And this is the focal length, which is the distance between the surface of the mirror, which is P, and F. Okay? Also, the law states that the radius of curvature is equal to twice F. This is the theory. In your case, you already have the radius measured. This is the radius. And you have the focal length measured. So you measure the radius here and the focal length here for the concave, and then you repeat for the convex. And you can compare, is R equal to 2F? What is the relationship? Do your results confirm your answer? And probably do the percentage difference and discuss. This is a general question, and here they want you to repeat the whole thing for a convex mirror. They want you to use a compass. You don't have to use a compass. You can use a regular ruler to be able to tell. Okay? So that's part 2, and experiment 1 is over. Part 1 was flat mirror, part 2 was spherical mirror. Do you have any questions? Please let me know before I proceed.
Yes, Doctor. كيف نعمل percentage difference؟ يعني ما معنى إلا one value.
All right, so I'm going to say R theoretical is equal to 2 times F. Okay? And R experimental will be measured by the ruler if you want. So this you measure with the ruler, this you calculate from the equation, but أكيد you have to plug in F experimental. So in other words, you compare 2 R's, both are experimental, but one measured directly and one taken from F.
Okay.
All right.
Okay, thank you. Thank you.
Yeah, but the values will be very, very close. You will see, because you don't have a lot of errors in this experiment. Like you don't have sensors and measure. You only have a ruler and a pencil, and that's it. All right, now experiment 2, Snell's law. In general, you are given a surface of separation between two media. This is a transparent medium, and this is another transparent medium. The difference is the index of refraction. They have different index of refraction. This is the incident ray. This is the refracted ray. This is the normal to the surface. Theta 1 is the angle with the normal. Theta 2 is the other angle with the normal. And this is Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. That's general. Now in real, you have this weird setup. You are given a piece of glass. Light ray will be shown on this surface. Okay? So you're gonna say this is incident ray, this is angle of incidence. You can draw the surface, you can draw the ray, and you can deduce the normal, and you can measure theta I easily. But you cannot see what's happening inside the glass. Nobody can see what's happening inside the glass. But you can see the ray that is emerging. You draw the emerging ray, and you draw the surface of the prism, and you remove the prism. And with a pencil, you can join this point to this point to tell what's happening inside. Okay, so you cannot see what's happening inside. You have to deduce it later after joining the initial ray to the final ray. And let me use dark blue to show you that this is theta 1 and this is theta 2. Not this one. This has nothing to do with the refraction because this is the surface I need to talk about. Okay? Now you have to do this for three trials. Like keep on rotating your prism or just move the light box. Find the angle of incidence, angle of refraction. Use Snell's law to find N. All right, what is N1, what is N2? N1 is N for air. It's equal to 1. N2 is N for glass. It's not known. So your job is to find N2. So you use Snell's law to find N2. Then you do another trial. You find N2 again. Then you do another trial. You find N2 again. Then you find the average. And then they want you to compare the average with an assumption that N should be 1.5 for glass. And then comment precision, accuracy, list the sources of errors, and answer a random question related to your observation. That's experiment 2. Done. Any questions? I'm waiting for you to respond.
No, doctor.
No, doctor.
All right. Thank you. Dispersion. I want somebody to volunteer to try to define dispersion.
Spreading of light.
All right. How does it happen?
When the light enters from one media to another, it causes the dispersion.
Okay, and for you, dispersion is separation of the different colors.
Yeah, that's what I mean. Yeah, more.
All right, and that's Joe talking. Anyone, Joe or anyone else, can explain why this happens? Sounds so interesting, but why does it happen? How come a single white ray will separate into the colors of the spectrum of light?
It's because the index of refraction is a function of the wavelength.
All right, so this is what Jana is saying. Also, Sherbel is saying that lambda changes. Anthony is saying that spreads light into different wavelengths. So obviously, the different colors, they have different wavelengths. And Jana just explained something very interesting, that each color has a different index of refraction. Didn't we say in this slide that N is equal to 1.5 for glass? We forgot to say that this is only applicable for yellow, because if you really look for different values, yellow is 1.517. For red, it's 1.515. For blue is 1.523. And this very slight change or difference in N will actually induce a slight change in the angle that would be visible to the naked eye. All right? So from now on in the course, when they give you N, you must know that this is only applicable for yellow. And if you Google index of refraction of different material, read at the top of the table. It says this is only applicable for yellow. All right? And if they ever give you 1 decimal, it means they're trying to round it up for all the colors in the spectrum. All right? Also, I want you to notice that you have 2 refractions in here. You have a refraction happening at this surface and another refraction happening at this surface. And this will amplify the dispersion. Like for the first one, you will have a tiny dispersion that may not be visible on the naked eye. And here it will get amplified because you will have a bigger deviation of the different colors. All right? This is the experiment you will do. This is exactly how you will be holding the prism on the table and white light, and you will keep on rotating your prism until the white light starts splitting into different colors. You cannot see 1, 2, 3, 4, 5, 6. I can see 6 colors on this diagram. In the lab, you barely can see 3. I don't know in the video. I'm gonna try to do a very good video with the lab being perfectly dark. I don't know if my regular iPhone will give me a good video or not, but probably you will only see 2 colors. So when they say what colors do you see, don't be crazy and don't list 8 or 9 colors. You can barely see 2. In what order? Just say the order you see on the video. Which color is refracted at the largest angle? Look at the figure and check which one is refracted more from the normal. Be careful. And then they want you to use Snell's law to discuss N versus the wavelength versus the fact that why red or purple has been diffracted more or less. All right? And here they want you to, here they want you to use 3 primary colors. Yani use your light source, not on white, on 3 colors and see what happens to those colors. Okay? So that's experiment 3, done. As you can see, no measurements is needed, only observation. Cool? Is that cool? Yes.
I have a question.
Yeah.
The number 6 refracted at the largest angle, as the angle of refraction, which deviation angle?
Good question. Aren't they the same? Let me see. If I draw the normal in here and I consider this surface, okay, the angle of refraction is this. So I see that red gets refracted, purple is refracted more.
Yes. قصدي بقلب الجلاس لأن فيه 2 angles of refraction.
Okay, so inside it's really blurred. Ah, you mean from glass to air or from air to glass?
Yes.
Good question. This one should be measured from here. No, answer from glass to air. And to be on the same side, start your sentence by, as I consider refraction from glass to air. So tell me where from. هن شو قصدون as you go out from the prism. So قصدون from glass to air. But you are totally right, Jana. If I consider air to glass, it's gonna be the opposite. Am I right or am I confused? No, you're totally right. Yes. So it doesn't matter what your answer is, as long as you state glass to air or air to glass, just for us to communicate well.
Okay, thank you.
All right, now I'm gonna move to experiment 4. Total internal reflection. I'm gonna give 2 slides for experiment 4 just to make sure you know what total internal refraction is. I'm gonna start with the first drawing. This drawing, which is here, explains the difference between if you are hitting critical angle or below or above it. Please keep in mind that light ray is traveling from water to air. Why from water to air? Because I need to move from a high refractive medium to a low refractive medium. Because if the opposite happens, you always have refraction. But from water to air, you don't always have refraction. You have 3 different cases. Let me assume that theta critical is equal to 42 degrees for water. I don't know how much is theta critical for water, but this is a way to calculate it. I'm gonna discuss it in a moment. If the angle of incidence is less than 42, you have regular refraction. But be careful, the angle refracted is greater than the incident angle due to the fact that N2 is smaller than N1. And due to the fact that n and sine theta are inversely proportional, so the bigger the n, the smaller the theta. But we don't really care about it as long as we know that we have refraction. Here, when the angle of incidence is exactly equal to 42, which is the critical angle, you have refraction, and the angle of refraction is exactly 90 degrees. Okay? Some books would say the refracted ray is grazing the surface or touching the surface of separation. If you have an incident ray angle bigger than the critical angle, you do not have refraction, you only have reflection. We call it total reflection because we always have a very faint reflection, but here it's totally reflected and it's not faint. It's really a strong brightness of a reflected ray. We call it internal because it's inside water and it stays inside water. It's not allowed to escape the water. So it stays inside. That's why we call it internal. So total internal reflection, okay? This is a diagram, I'm sorry. This is a diagram, let me just zoom in a bit. Okay, that shows you the incident ray, the reflected ray, and a refracted ray at 90 degrees angle. This is theta critical because at theta critical you have 90 degrees, right? This is the reflected ray. It's always there, it's very faint. This is theta 1 and this is theta 2. They should be equal. So if this is theta critical, this is also theta critical, and the whole thing will be 2 theta critical. This is just saying. All right, if I use Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. n2 is for air, it's here. It's gonna be equal to 1. And this one is not known. Theta 1 is theta critical. Theta 2 is 90 degrees. Let's do the calculation. Probably Jana can help me. Jana, if n is equal to 1.5, what would be theta critical? Can you do the calculation for me? I'm referring to this equation that came from this Snell's law. Do you have a calculator on you? I heard 40 something.
Theta critical 41.8.
41.8 degrees. All right, very close to 42. Not that I didn't know, because in the first session they said 41.8. All right, so yes, it makes sense. So this is a method for you to calculate theta critical. You take the angle of incidence to be exactly equal to theta critical. Theta 2 will be equal to 90 degrees. All right. Which means that you can simply plug in the values in Snell's law to be able to find theta critical. All right. Now let me check the experiment. You will have this case, figure 1. You will shine light exactly in this, like in this scheme. Incident ray, refracted ray, that is also an incident ray to this surface. And then you have refraction here, and this is a reflection. You keep on turning your prism clockwise until the refracted ray disappears, but not disappears at all, totally. Let it be like that, grazing the surface. Because whenever it's grazing the surface, you guys, am I having internet issues? Can you hear me? I should be clear. Okay, I'm not being. Are you being able to hear me?
Can hear you.
Okay, you are hearing me. That's good. Am I sharing my screen? Share screen. All right. Can you hear me now?
No.
No.
Yes, but I'm late. I think it's late. It's a bit laggy.
It's okay.
Like
probably the internet connection is taking a break. You know, it's nap time now for internet connection. That's so silly. I hate it. All right. I turned my camera off on purpose just to make sure you guys can hear me. I'm sure things are gonna get either better or worse. No, أكيد يا better يا worse. All right, I'm just being sarcastic because I hate this. Anyway, I'm gonna continue a bit. So you're gonna rotate your prism in such a way for the refraction to be grazing the surface, يعني just before it disappears. And this is where you have theta critical for the angle of incidence. Like if I draw the normal like this, let me draw it well. This is the normal. Okay, this is theta critical. And this is another theta critical because incident and reflection are equal. That's why it's written here 2 theta critical. So this is a method to find theta critical, is to measure all this angle inside and divide it by 2. By the way, you cannot draw the rays inside. What you can draw is, you can draw the prism using a pencil. You can locate this point, and locate this point, and eventually remove the prism, and with a pencil you can join the lines, and then you measure what's inside. All right? Cool. Now the next slide, what you have, they show you again how you started with figure 1, and they actually show you how you rotate it in such a way for the refracted ray to simply disappear, just disappearing, and how you can see 2 theta critical. Experimentally, they want you to write theta critical, and you will definitely measure it from here. Theoretically, you can find theta critical using this equation. N sine theta critical is 1 sine 90. I think N is given. If it's N is given. So, and then you compare the experimental to the theoretical, and you comment, and you answer some questions. All right, and that's it. Now, to make this really meaningful, we need a very good video. So, which means you don't have a deadline. In other words, the deadline you have here is only tentative. You don't have a deadline until I post the video. And when I post the video, I'm gonna post the deadline for you and confirm this one. And probably 2 days are not gonna be enough, and I'm willing to extend it, because the point is not to eventually give you a very strict deadline. The point is just for me to finish lab 7 today, even if I don't have a video of it. Okay? You guys can hear me, or am I talking alone? Yes, you can hear me. All right. So that's it for today. I'm gonna stop recording, but I'm staying because I'm sure somebody may have a question.